Harmonics means that voltages of higher frequency are also present in addition to the voltage of the fundamental frequency. The harmonics are caused by a non-sinusoidal flux. Harmonics increase the skin effect, they increase the core loss, they produce retarding torque and cooling in the induction motor. We will see later in this video that even in Triplon harmonics are absent in the star connected stator winding. Higher harmonics are lesser in value and may be neglected. Hence, we need to concentrate on the fifth and the seventh harmonic. Harmonic can be reduced to a limited extent at the generator end. More efforts are required at the load end, say by installing harmonic filters. Harmonic filters need not be broadband. These may be suitable to reduce fifth and seventh harmonic only. Harmonics means that higher frequency components of the voltage are also present in addition to the fundamental frequency. In the case of 50 Hz supply, second harmonic means that there is a voltage component of 100 Hz and third harmonic means that there is a presence of voltage of 150 Hz. Harmonics are caused by the distortion of the flux phi. Induced EMF is proportional to d phi by dt. Hence, distortion of the flux leads to the distortion of the EMF. Flux is distorted due to nonlinear load, slot harmonics, saturation of flux, etc. Let us examine these factors one by one. The variable frequency AC drives are fast replacing the DC drives. These drives use thyristor. Thyristor starts conducting after it is triggered. Load current, which is equal to the armature current in a star-connected stator winding, is distorted. This leads to the distortion of the flux. EMF induced, which is equals to d phi by dt, is also distorted. Stator is slotted to accommodate stator coils. This results in the variation of reluctance around the stator core. Reluctance at the teeth portion is less than that in the slot. Flux in the tooth portion is more than that in the slot. Hence, the flux is distorted. MMF waveform, which is produced by the rotor field winding, is sinusoidal. The flux becomes flat due to the saturation. This results in the distortion of the flux. As for the Fourier series, any periodic non-sinusoidal waveform is a sum of the fundamental and harmonics and is given by A1 sin omega t plus A2 sin 2 omega t plus A3 sin 3 omega t and so on. Let us examine the second harmonics. If one coil side is under the north pole, the other coil side is under the south pole. In the case of the fundamental frequency, EMF induced in both the coil sides aid each other. In the case of the second harmonic, since voltage is running 2 times faster, direction of EMF in both the coil sides is same. These EMF oppose each other. That is, these cancel each other. This is applicable for all even harmonics. The even harmonics, that is second, fourth, sixth harmonic, are absent in a synchronous generator. Let us examine the third harmonic. Third harmonic means that these are running 3 times faster. By the time the fundamental completes one cycle, these complete 3 cycles. Let us take an instance A. In case of the third harmonic, there is no voltage difference between R, Y and B phases. The Triplon Harmonics, that is third, sixth, ninth harmonics, are absent in the Star Connected Synchronous Generator. We have seen that even harmonics are absent. In a star connected generator, Triplon harmonics are also absent. Higher harmonics are lesser in magnitude and may be neglected. Hence, we need to concentrate on fifth and seventh harmonic only. There are various effects of the harmonics. These create skin effect. Skin effect means that in the case of AC current, more current flows on the surface, that is skin of the conductor. The current reduces drastically when we move from the surface to the center. Skin depth means the distance from the surface where current reduces to 37%. As the frequency increases, skin depth decreases. Effectively, the current flows through a lesser area. Effective resistance increases, resulting in more I square R drop, increasing the temperature. In the case of the fifth harmonic, skin depth reduces to half as compared to the fundamental. Effective area through which current is passing reduces to half, and hence I square R drop doubles. The iron loss is equal to hysteresis loss plus eddy current loss. Hysteresis loss is proportional to frequency, and eddy current loss is proportional to frequency square, and hence iron loss increases with harmonics and temperature increases. Let us see the effect of the fifth harmonic on the induction motor. Phase sequence in the case of the fundamental frequency is RYB. In the case of the fundamental frequency, flux rotates in the RYB direction. Hence, torque will be in the RYB direction. The fifth harmonic is running 5 times faster. That means that when the fundamental completes one cycle, the fifth harmonic completes 5 cycles. Let's combine the waveform of the fifth harmonic. Phase sequence in the case of the fifth harmonic is RBY. The flux will move in the opposite direction with respect to the fundamental. The torque produced by the fifth harmonic opposes the main torque. Now let us do the same exercise in the case of seventh harmonic. Flux of seventh harmonic runs 7 times faster. The phase sequence in the case of seventh harmonic is RYB, which is same as that of the fundamental. The direction of the torque produced due to the seventh harmonic is same as that of the fundamental. Let us superimpose torque speed curve of the seventh harmonic on the fundamental. A dip is created in the torque speed curve. The load curve may cross this dip. The induction motor starts running at 1/7 the rated speed. we say that the induction motor is crawling. There are various methods to reduce harmonics. As discussed earlier, flux is distorted due to saturation. Flux can be made more sinusoidal by the proper shape of the poles. Air gap is increased at the pole ends, resulting in the increase in the reluctance. This reduces the flux at the pole ends. This makes the flux more sinusoidal. This method is not applicable in the case of the cylindrical rotor. Harmonics can be reduced by increasing the air gap. This results in the reduction of the slot harmonics. However, more MMF is required to develop the required EMF. This increases the size and the cost of the generator. Distributed winding reduces harmonics. Phasor of fifth harmonic runs 5 times faster. Phasor of seventh harmonic runs 7 times faster. The resultant EMF in the case of fifth and the seventh harmonic reduces due to distributed winding. Distributed winding has got added advantage. Current and temperature are evenly distributed around the stator core. Let us calculate the distribution factor in the case of fifth and the seventh harmonic. Formula of the distribution factor is given. In the case Q is equal to 3, distribution factor in the case of the fundamental frequency is 0.96. In the case of fifth harmonic, it is 0.22. And in the case of seventh harmonic, it is 0.18. Phasor diagram of the fundamental fifth and the seventh harmonic is shown. As seen, the fifth and the seventh harmonic reduces with the short pitch winding. The short pitch winding also reduces overhang length of the winding, reducing the length of the generator. The formula of the pitch factor is given. Short pitch angle of 30 degrees is the most suitable angle to reduce both the fifth and the seventh harmonic. The pitch factor in the case of the fundamental is 0.97 and in the case of fifth and the seventh harmonic is 0.26. At the generator end, there is a limited possibility to reduce harmonics. If we reduce the fifth harmonic, seventh harmonic increases, and if we reduce the seventh harmonic, fifth harmonic increases. Main source of harmonic is nonlinear load due to thyristor drives. Harmonic filters may be used to reduce these harmonics at the load end. Harmonic filters suitable to reduce fifth and seventh harmonic is sufficient. There is no need to use a broadband harmonic filter.